Okay. If I've got a bar moving in a magnetic field, positive and negative charge are going to be shifted, redistributed, so that there is a potential difference over that bar. What happens if I give that charge some place to go? The hypothetical for this is to imagine that this bar is free to move on frictionless rails connected by a wire, which means that as this bar is moving through this electric field up, it will set up an EMF in that bar, and it will give rise to a current. Let's see, positive here, negative here. So the current will flow in that direction. I establish, whoops, EMF's in the other direction, so it'll establish a current in that loop. Now, if I look at what I've got here, what can I say about this? Okay, I can say that the current in that loop is equal to the induced EMF in the bar divided by the resistance of the resistor R. If the resistance of the resistor is much higher than the resistance of the wires, very easy to set up, and we're dealing with an ohmic material, I keep saying this just so you know that this isn't that Ohm's law here, it's not a universal truth, but it's a mighty darn common truth, and it's certainly what we're going to be looking at. Now, what is that induced EMF? Well, the induced EMF is the change in potential from one end to the other of the bar. So, that's equal to the integral over the path of E dot dl as I go along the bar. Well, what's the electric field? The electric field, if you look back at the last bit of work we did when we were simply looking at the bar, the electric field strength is equal to the velocity of the bar times the magnetic field that it's in. We rewrite the electric field like this because the velocity and the magnetic field, those are things from the situation that, at least in this way of looking at it, we know from the beginning. And dl is just some differential path length. Now, the electric field is either parallel or anti-parallel to the path, depending on how we go. So the dot product just is E dot dl is simply E times dl. So, the change in potential, which is the EMF involved here, is equal to the velocity times the magnetic field times the length of the bar. Therefore, the current, and this is generating the wire, is equal to the velocity times magnetic field strength times the length of the wire L divided by the resistance R. Now, we're not entirely done here. And the reason why we're not entirely done is because since I've got a current in this bar, I'll feel, this bar will feel, there's current going through each of these sections. Each bar will feel a magnetic force due to that current. It will feel a magnetic force equal to QV, for a current, that would be I delta L cross B. Now, if I've got the current going upward and B going into the board, then I will feel a magnetic force resisting the motion of the bar. So if this bar is sliding and all of a sudden, bling, I turn on a magnetic field, then yes, the bar moving in a magnetic field will cause a current to flow through this loop. But the fact of the current flowing through this loop will mean that this bar will feel a magnetic force on it, slowing the motion down. So if I want to keep this bar moving, I've got to have something else on the other side, pulling with a force to even that out. Or to put it another way, this is a very important conclusion from this discussion. The force, I've got something that's changing. The position of this bar is changing. The force, the magnetic force that will result from that motion in a magnetic field, resist that change. Let me see if I can find a place to write it notably so. The force let's see. The motion of the bar results in a magnetic force opposing the motion.